the LUCI lab for the invitation. This talk is based on joint work with Mario Piazza for the first part and Mario and Gabriele Pulcini for the second part. I don't know if I will have time to present both parts with the same degree of detail, but I will try to. So let me start with a general remark on the kind of approach that I will present here. The main intuition we start with is the idea that in non-monotonic reasoning you have an interplay between probability and refutability. Okay, you prove something, you deduce something, provided that something is not proved, provided that something cannot be deduced. Okay, is not deduced, sorry. And the idea is to give to this intuition a Gensen style rendering by means of sequence for probability and sequence for refutability, namely anti-sequence, okay? Exploiting what in the literature has been made about refutation theoretic calculi. The idea is to combine sequence and anti-sequence into suitable Gensen-style calculi and thus to try and give a uniform platform, proof theoretic platform for different kinds of non-monotonic reasoning. I use reasoning instead of logic because I include abduction, which cannot be labeled, is not usually labeled as a logic, but as a kind of reasoning, okay? So in the first part, I give some preliminary notions and results on default logic, and then I will skip to the presentation of the first kind of calculus, which capitalizes on the intuition, sequence and anti-sequence interacting, okay? So I assume that you are all familiar with what default reasoning is, drawing conclusions under incomplete information and in absence of explicit evidence to the contrary. The standard toy example deals with Tweety, which is a bird, and which flies, provided that it is not a penguin. I assume that you see the slides correctly. Am I?
Yes.
Okay,
Yeah,
okay,
you're right.
perfect.
Thank you.
Thank you. So, more formally, default reasoning is treated with domain-specific inference rule of this form. You can see B is the prerequisite, let's say the premise. You have some justification, some non-contradictory formulas that should not be proved. And you have typically a non-tautological formula as the conclusion, and the intuitive interpretation of a rule like that is if B is proved, then D is provable as far as the negation of C1, the negation of Cn is not provable. Standard terminology, if n is equal to 1 and the only justification is equal to the conclusion, the default is normal. And I use supernormal to intend a normal default, which is prerequisite free, and semi-normal, as in the standard case, when the only justification is the conjunction of the conclusion and another formula, a non-tautological formula. So a default logic is just a pair of a set of extralogical axioms and a set of default rules. We assume that both sets are finite, and in particular that the set of extralogical axioms is consistent. That is a reasonable assumption because we would like to model an ideal agent who deals with information, but who does not that who does not that in a trivial way, and so the main point that we have to deal with at this stage is to isolate the notion of extension we are interested in. An extension is just a set of formulae derivable from extralogical axioms by classical logic and application of default rules, by maximal application of the underlying rules, okay? According to whether we adopt one notion of extension or another, we put ourselves into different variants of default logic. This is standard, and maybe most of you are familiar with these notions, but I will recap them. So a writer extension is just a set of formulae derivable by maximal applications of the rules of the logic. And in particular, maximal application of default rules whose consistency condition holds both before and after they're being triggered. Okay, so if you look at the definition below, it is a circular definition because you notice at first glance that the definiendum occurs in the definiens. And the idea is that you have to backward check at any time if all consistency conditions of default rules applied so far are still respected. So you start from extralogical axioms, then you take the conclusions of triggered default rules, provided that the negation of the justification is not provable so far. Okay, but that so far is both extends in time, both before and after application. Okay, this is somehow this could remind some future conditionals where the antecedent deals with something which happens in the future of the consequent, okay, something like that, okay. And you define on top of this notion of extension two notions of consequence relation, credulous one, which corresponds to inhabitation of at least one extension, and the skeptical one, which corresponds to inhabitation of all extensions. There is another notion. We will rely on this notion in particular for the hypersequent calculi because it is far more well behaved with respect to crucial properties. That is the notion of Lukashevich extension or modified extension, where you have to where the extension is defined by quasi-induction, by simultaneous quasi-induction on two things. The extension proper, the set E, and a support set F, which collects all the justifications of default rules that applied so far. And the idea is that you have a consistency check for any default rule applied at a certain stage, which regards the conclusion of the default rule just applied and the justification of the rule just applied as well as rules previously applied. Okay, so that, for instance, you cannot have a default rule concluding a formula which contradicts the justification of the rule itself. Okay, so this limitation that is encoded in the inductive step of the construction allows you to avoid certain circular situations in default applicability. Here it is an example. If you look at the second example in the slide, you have that the first, if you stick to the first notion of extension, the writer's one, then you have that the default theory has no extension, because for any extension, if not P belongs to the extension, then not P does not belong to the extension, okay? Because to reach not P, you violate the consistency condition. But if we withdraw not P, then nothing prevents us from applying the default. So we are stuck in a circular situation, which is somehow reminiscent of the liar's paradox. Okay, it's a bad kind of circularity. Okay, whereas in the Lukashevich approach, you definitely you are prescribed not to apply the default rule. So you stick to the ground level, so to speak, of things that can be obtained from the extralogical axioms. You just take as the modified extension tautologies, because in this case you have an empty set of extralogical axioms. And again, maybe you are familiar with these properties, but I recap them. So the first point will not concern us because we have limited ourselves, we have confined ourselves to consistent sets of axioms. But if we had inconsistent sets of axioms, then we would have also inconsistent modified extensions. And again, this argues in a way for the assumption that we have made for the fact that it is reasonable to accept consistent sets of extralogical axioms. Then you have the second point, the property which can be called confirmation by evidence. If you get to something into an extension and you add up to the extralogical axioms what you have obtained, then what you have, the extension you had in the first time is an extension also of the extended theory. Okay, you build on evidence. Okay, in this sense, you cannot do the converse. Okay, and that has been famously shown by counterexamples put forward by Mackinson. I will return on this point. For normal default logics, modified extensions and writer extensions coincide. And the last property is a maximality property. If you have an extension and that extension is component-wise included into another extension, then the two coincide. Okay. As a consequence of these properties, you have properties on the consequence relations, on the credulous and skeptical consequence relations. Okay. And in particular, you lose cumulativity. The fact that if you add consequences to the set of premises, you change the set of consequences. Actually, things are a little more nuanced, because you have that, and this is the second point you see in the slide is not usually emphasized in the literature, but I think it's worth mentioning. Credulous consequence satisfies a very weak form of monotony. By confirmation of evidence, that is the property we have seen before, if you have that B1 inhabits one extension and B2 another one, then if you add there disjunction, a very weak additional premise indeed, then you keep obtaining either of the two, okay? B1, B2, okay? And that's, if you take B2 to be the absurd, this principle has somehow a Popperian flavor, because if you, from a theory, you get into the absurd, then you cannot save the theory from the absurd by adding a consequence of the theory, okay? Then we have that skeptical consequence always satisfies cumulative cut. So you see that they fail to be cumulative, but in different ways. Okay, you see at this point that credulous consequence does not always satisfy cut, and skeptical consequence does not always satisfy cautious monotony. This one, I think, still open problem, if one is interested in it, is to find representation theorems for default logics in the style of KLM logics. If you can define suitably designed preferential structure or something like that, that can represent in a strong sense default logics. Okay. And then we have last step, some crucial results about Łukasiewicz default extensions. We will capitalize on these results. The first one is of the greatest importance, because we have that for any default logic, we are guaranteed that the notion that the credulous consequence is well defined. Okay, that we have at least one modified extension. Okay, and the second point is crucial for the proof of adequacy of our hypersequent calculi. Says something which can be rephrased like this. If you have a default logic, then for any modified extension, there is at least one modified, larger modified extension. There is at least one modified extension including it, of a Sapra theory where you have added up default rules. Okay, so it is a monotonicity with respect to the addition of default rules. For instance, default rules that have not been applied so far, okay, along a derivation. That will be our application of this property. And the last one is a result by Marek and others, which says that we can give a kind of normal form for defaults. So if you have a conjunction into the conclusion of a default, you can replace that default with defaults that have a single conjunctive conclusion, ceteris paribus, in the sense that the prerequisite and the justifications are just as the same. Okay. So at this point, nobody lives in a desert, and proof theory for the propositional default logics makes no exception. There are previously attempts to give, most notably, Gensen-style calculi for propositional default logics. We see as an unsatisfactory feature of this Gensen-style calculi the fact that they rely on ad hoc extensions of the underlying language. You have to introduce a connective for the default rules, which behaves in an ad hoc way, and then you have to add a model operator to keep track of inhabitation of extensions. So in a way, this calculi, however good as far as the scope of application is concerned, presents some undesirable features. They can be seen as decision methods for the consequence relations, but we would like to do something different. From the constructive point of view, instead of sticking only to the parse destruens, so to speak, we would like to provide a modular and uniform platform for extensions of classical logic, both monotonic and non-monotonic. We would like to be as modular, as uniform as possible. So let's introduce the formal apparatus. This calculus you see here has been first introduced by Klein in mathematical logic with the name of G4. It's just G3 of Trustra-Schwichtenberg's handbook. We adopt context as multisets as it is standard. We use theta lambda to vary. We use theta lambda to denote multisets of atomic sentences, atomic formulas, sorry. And this calculus is well known, has all the good properties. Bottom up is just Asmalian tables, Asmalian slide, sorry, tableau. And you have all good proof theoretic properties: admissibility of structural rules, height preserving invertibility, termination of proof search. Now, this nice calculus can be smoothly used to treat not only classical validities, but also classical invalidities, okay? Take, for instance, a configuration of symbols where you have on the left-hand side a set of multi-set, sorry, of atomic formulas, and on the right-hand side another set, such that their intersection is empty. Okay, if you take the formula translation of this kind of sequence, let's say, of these two sets separated by a turnstile, then what you get is a classical invalid formula. So, generally speaking, whenever you reach a leaf where let's say a complementary leaf, okay, in the proof search for given us a sequence where you have atomic formulas on the left-hand side and atomic formulas on the right-hand side with no intersection, with empty intersection between them, then you're sure that the formula translation of the sequence that you started with is classically invalid. Okay. If you rewrite G4 logical rules prioritizing anti-sequence, as you see for the right rule for conjunction, you get a calculus which we call G4 double barred, and which is just a calculus which proves classical validities, and gives a derivation of anti-sequence whose formula translation are classical invalidities. We say that a derivation ending in an anti-sequence is a refutation. So that's the reason for the title, proofs and refutations. And of course, probability and refutability are sound and complete with respect to classical validity, classical validities and classical invalidities, respectively. I will use with asterisk in apex for the turnstile this symbol to vary over sequence and anti-sequence. And well, G4 double bar can be used as a mechanism to decompose any formula, any sequence, okay, so as to reach atomic sequence, anti-sequence, both sequence and anti-sequence, okay. The nice thing is that if A is classically invalid, then you have a canonical conjunctive normal form for A. So we can use G4 double barred as a mechanism to pinpoint at a specific conjunctive normal form of a given formula. That's the main use we will make of this calculus. And then we can adapt G4 double bar calculi for G4 double bar calculus for the case of supraclassical logics, where by supraclassical logic we mean a finite consistent set of extralogical axioms, just like we did at the very beginning when we defined the default logic. So we drop uniform substitution, we take propositional variables to be propositional constants instead, but what we get is an extension of classical logic where we have extralogical axioms, okay? Let's say information about the world, that's the reason why we use W. So we can decompose the extralogical axioms into clauses, and then we can close this set of clauses under contraction and cut by simply applying, recursively applying and maximally applying this procedure. You take the closure under contraction of a set, you perform a single cut, and then you add the result of performing cut, and you keep going, okay, until you're stuck. By this notation, top star C, I will denote the complementary clauses that one obtains after application of this procedure. I remind you that the complementary clause is a non-identity clause. It's a clause where you do not have both a literal and its conjugate. So we can obtain G4W double bar calculi for supraclassical logics by simply substituting some anti-sequence with sequence. Something which was not provable at the level of classical logic becomes provable at the level of a given supraclassical logic, provided that, of course, the set of extralogical axioms is not empty. So, some terminology. Admissibility is just as in J4 double barred. Something is provable if the conclusion is provable. A rule is admissible if the conclusion is provable whenever the premises are provable. Absorbed when the conclusion is derivable whenever the premises are derivable, where derivability does not coincide with probability. You can derive an anti-sequent. And pure, I borrow terminology from a work by Avron, if it is admissible, if the rule gamma 1, delta 1, we say that the rule gamma 1, delta 1, gamma n, delta n, gamma delta, that you see on top of the slide, is pure if it is admissible exactly when it is admissible another rule which I obtained from the given one by adding arbitrary context to the premises and having them preserved into the conclusion. This is something that has to do with reasoning by cases, after all. Okay, I can weaken the premise and then I will obtain a weakened conclusion. Okay. And I will say that G4 double bar, G4W double bar, sorry for the pun, is pure exactly when all its rules are pure. And for G4W double bar calculi, all rules are pure. I introduced this notion of purity because we will see that in hypersequence we will lose purity. So let's, as you may, there is no surprise in this. We have designed these calculi so that they enjoy good structural properties, and in particular admissibility with preservation of height of weakening and contraction. Strengthening is just the inverse rule of weakening, where you permute conclusion and premise, and you change from sequence to anti-sequence. You have invertibility of logical rules, admissibility of cut, and what is most important, full subformal property, in the sense that if you derive something, then anything used in the derivation, any sequent or anti-sequent used in the derivation contains formulas which are subformulas of the formulas including which occur in the conclusion. Okay, and as far as admissibility of cut is concerned, the strategy is standard. You make double induction on complexity of the cut formula and some of the height of the premises of the topmost cut, until you have that the premises of the cut are initial sequence, and then you prove that the set of all initial sequences is closed under cut. By the way we have designed our calculi, this is a natural consequence, because we have taken, if you remember, the closure under contraction and cut of the clauses obtained by the composition of the extra logical axioms. Okay. Okay. And just another remark on this calculi, which is useful when we compare this calculi with the hypersequent calculi I'm just about to show you, is that purity of rules coincides with something that has to do with ultimately deduction theorem. I've called it deductive completeness in lack of a better name. Okay. Any G4W double bar calculus is deductively complete in the sense that derivability, better probability, within sequence can be encoded into a single sequence, into a single provable sequence, and vice versa. Okay, and we can prove, the proofs is a generalization of a result given by Avron, is that deductive completeness, as I say, and purity stand or fall together. Okay, there is an if and only if between them. Okay, and the proof relies on the proof theoretic properties, the nice structural properties of the calculi. Okay, so we are ready to present a tailor-made notion of hypersequent. Okay, I will present a somehow non-standard notion of hypersequent. Typically, hypersequents are lists or in most cases multi-sets of sequence separated by a bar, and the intended interpretation of the bar is disjunctive, so that if you prove a hypersequent gamma 1 turnstile delta 1 bar gamma n turnstile delta n, then you are proving a formula which is the disjunction of the formula translations of all the sequencing occurring in the hypersequent. Okay, the hypersequence have been introduced to give analytic presentations of intermediate logics and modal logics and other non-classical logics that lacked cut-free sequent calculi. We rephrase the notion of hypersequent, and as you may expect, we make within hypersequence interact the sequence and anti-sequence, so that a hybrid hypersequence, as we call it, is a set made up of a sequent and a possibly empty set of anti-sequence. Okay, The intended interpretation that is crucial of a hypersequent like that, a hybrid hypersequent, is conjunctive, in the sense that the bar represents a conjunction of conditions on probability, a positive one, which is represented by the sequent, and possibly non-negative ones represented by the anti-sequence, okay? So the idea is that you keep in parallel sequence and you want all of them to hold in a certain way. That's in a nutshell the idea. And well, the conjunctive interpretation of the separating bar is not entirely new. It has already been exploited by Poggiolesi and others. I do not recall the first author, for intuitionistic logic of proofs, Artyomov's Artyomov logics of proofs, and by Mario Gabriele and Matteo Tesi for the multiplicative additive fragment of linear logic. So we capitalize on this new reading of the separating bar with a new feature, as far as we know, that is the parallel composition of sequence and anti-sequence. We call the anti-sequence in a hybrid hypersequent as the refutational part of the hypersequent. And then the calculus. The calculus has this form. I make some general comments and then I will illustrate the rules because it's important, and in particular the last one, the last ones, okay, that you can see in red. You can see that binary rules, as far as refutational parts are concerned, have a multiplicative flavor because you merge the negative prescriptions of premises into the conclusion. And you can also see that the only rule which adds new negative prescriptions, new anti-sequence in the refutational part of the conclusion is the last one, is the delta one, okay? Okay, maybe I can skip to the following slide. Of course, we must say something about the rules. So let me start with the axiom, the axioms. Okay, you see theta lambda, where theta and lambda may have non-empty intersection, so as to cover the case of identities, as well as non-empty intersection, yes, and also they may have empty intersection as far as theta lambda is a clause belonging to the decomposition further elaborated, further processed of the extralogical axioms. So by this, I want to incorporate, with this rule, I want to incorporate the extralogical axioms. You see, no, you do not see in the formulation of rules, but I tell you that this rule, for each HG4 calculus, you have a distinct set of anti-sequence which must occur into the refutational part of initial sequence. Okay, so each HG4 calculus will have a refutational part included, and another one, a distinct one, so on and so forth, for all possible choices. Okay. And of course, the refutational parts of the initial hypersequence are preserved into the conclusion. So and possibly with possible additions due to the application of delta rules. So you may notice that our formulation of the X rule absorbs what is called in the proof theoretic literature external weakening with respect to refutational parts. And then the delta rules. The delta rules are designed to directly capture default rules. Okay, so I've used colors to make it clearer. I hope so. If you have a prerequisite B, then you decompose it. You have the algorithm to do that. You pre-process your default logic. Remember that normal form result we started with. You can split the conclusion, the conjunctive conclusion of a default into several defaults, each having as conclusion a single conjunct. So you pre-process modulo modified extensions, your default logic, and then you get a single clause as conclusion of any default. So you have this this 5 psi as conclusions. There may be more than one because we close under contraction. The closer undercut is vacuous, but the closer under contraction may not be so. And then you have a rule which has a derivation of the prerequisite, better of the clauses in the decomposition of the prerequisite. That's for the right premises. For the left premises, you have a weakened version where you have the arbitrary constants gamma and delta, and the repetition of what will be the principal formulas, the formulas that will be the conclusion, okay, that will represent the conclusion of the default. This repetition is not needed. Is not needed as far as admissibility of structural rules and soundness and completeness are concerned, but it's a nice feature we would like to keep at least as a first approximation. I will return on that. And then for prerequisite free rules, you have another way of doing the same thing we are doing now. And then you have further conditions on the extra logical rules, which are, I will not enter into the details. If you are interested, you may ask. These are closure conditions that allow you to prove cut elimination substantially. And they resemble the closure conditions you had for the extra logical axioms in supraclassical logics. Okay, you have to design the calculus so that it makes what you want it to make. You have a labeling system to keep track of the default rules that have been applied so far in the derivation, better, of the default rules corresponding to the extra logical rules applied so far. Okay, so you have this labeling system to precisely do that. And here it is an example, given a default logic of what the calculus looks like, of any HG for calculus looks like. You have the initial hypersequence, as you see, coming from the decomposition of the formulas in W. And then you have, for instance, take delta. You have an extra logical rule corresponding to the first default rule, which says that if you have proved P implies Q, and if you have proved P implies Q, possibly weakened with other stuff, including the conclusion, what will be the conclusion of the default rule, then you can obtain the conclusion, and indeed even a weakened version of it, provided that you merge the refutational parts and you add the suitable anti-sequence corresponding to the justification of the default rule. Okay, you have the labels, and the closure condition tells you that if you have this rule and these rules, in this rule, you see that S is a cut formula, is a possible cut formula. So you have to define another rule here where the cut has been performed, and all the premises of the two rules have been merged. Okay. So the first worry we have is to define a calculus which captures modified credulous consequence. The point is that the notion of derivation does not match the notion of derivability according to the credulous consequence. Because if you look at this example, you have PQ as extra logical axioms, and you have two rules that tell you to go to R1 and another one to not R, and you cannot apply both of them because otherwise you would violate one of the two negative conditions. So you have two extensions. One where you take the consequence of PQR, and the other the consequences of PQ and not R. Yeah, the point is that in the HG4C, I will say in a moment what is this C calculus. You have this derivation where you can derive R and not R, where R and not R, of course, is not a credulous consequence of the extra logical axioms. The HG4C calculus is just precisely that HG4 calculus, which has no restrictions on the refutational parts of initial hypersequence. Okay, so you want to restrict proofs, okay, sorry, derivations, so that to grasp what counts as a proof and what does not count as a proof. This is somehow reminiscent of what happens with proof structure in for linear in the proof theory for linear logic. Okay, so the idea is to well, to keep track by means of the labeling system, after all, of the default rules applied so far along the branches of the derivation tree, and then give a notion of soundness of the derivation, in the sense that it must conclude a hypersequent, where if you take the extra logical axioms you start with, and the additional assumptions you have piled up by means of application of default rules, then you do not prove anything which should not be proved, okay? Which is in the refutational part of the hypersequent, okay? So for instance, if you take the derivation of the example in the slide before, then you have that its immediate subderivation are proofs. The point is that if we apply the right rule for conjunction, we obtain a paraproof. And that can always happen with binary rules, by the way, okay? As well as with, of course, extra logical rules, as it is shown in this example. So you have that the derivability and admissibility do not coincide. The point is, sticking to this notion of probability, how can we prove that it is sound and complete with respect to modified credulous consequence? The answer for us is to perform structural analysis of the HG4 calculi. So we show that the rules of weakening are height preserving admissible by induction on the height, which is defined as usual. We prove that the logical rules are height preserving invertible, provided that invertibility is correctly defined. We have to keep track of the refutational parts, after all. So we have to say that the rule is invertible whenever the conclusion is provable, whenever if the conclusion is provable, then one of the premises is provable with an enlarged refutational part. Okay, as you see in the slide. Then we can also permute down logical rules with respect to astrological rules, so that proofs have a normal form. We apply astrological rules and then logical rules, and this gives us a natural proof search strategy, which will be a nice decision method for credulous consequence. Modulo adequacy, of course. We have to keep track of the loops generated by the repetition of principal formulas into left premises as far as extralogical rules are concerned, but that is not a preoccupation for us. The only point of this decision method, I will skip details, is that we have to minimize refutational parts, okay, during the proof search. And then we have the admissibility of contraction. Once more, we exploit the fact that we exploit the closure conditions we started with in the design of HG4 calculi. And then finally, we prove for cut elimination. Again, cut is a binary rule, so we may have cut applications which are not, such that the premises are provable, but the conclusion is not. So we limit ourselves to cases where indeed you have that you end up with a sound sequence. Okay, so we have a limited form of cut elimination. We eliminate all cuts that can be eliminated. Okay, and this has, of course, to do with the design of the calculus. The strategy to prove cut elimination is the same as followed for superclassical logics, for G4 W double bar calculi for superclassical logics. If the most interesting case, the most meaningful case is when the cut formula is atomic. Then if the cut formula is atomic and it is not principal, we permute the extralogical rule and the cut. And if it is principal, then we reason by cases over the last rule applied in the proof of the other premise, okay? And we have to exploit something, height-preserving admissibility of weakening, admissible instances of external weakening, and the closure conditions, okay? The calculi, because there is more than one, of course, for each default logic, enjoy a weakened version of the subformula property. As you may have noticed, when you have a derivation, let's take an example, for instance, this one, well, better another one, sorry, okay, better, okay. If you take, yes, this one, sorry, this one, what you have is that any hypersequent, I've missed the refutational parts here, not by chance because they are empty. So if you have this derivation, you see that any hypersequent in the derivation in its probability part, let's call it this way, has formulas which are either subformulas of the formulas occurring in the probability part of the conclusion or atoms. So we have a weakened subformula property like of the kind that has been obtained by Negri and von Plato for sequent calculi incorporating astrological axioms as rules, okay? So soundness and weak completeness, I will skip details because my time is running fast. So soundness and weak completeness, capitalizing on the proof theoretic properties of the calculi and crucially for the soundness on semi-monotonicity of Łukasiewicz default logics. That's why we used the Łukasiewicz default logics in the first place. Then AG4 calculi are sound and weak complete with respect to other, let's say, to extensions with primitive negative prescriptions. Okay, with the starting level of the support set not empty. And then we have that the calculi, however adequate in a weak sense, are not adequate in a strong one. And you may say that this is no surprise because we have admitted left weakening. Okay, so you have that the sequence keep track of derivable formulas but do not keep track of the consequence relations. So just to give you the sketch of what follows, you have of course that you lose purity and deductive completeness, and this has to do with the fact that you lose reasoning by cases and conditionalization at the level of these consequence relations. You have a decision procedure for modified skeptical consequence, which does not presuppose the computation of all modified extensions, and more interestingly, amounts to the exhaustive search of counterexamples via finite sequences of abductive inferences. So I think I have not the time to speak about abduction as I would have liked to do. Let me just say that the decision procedure for modified skeptical consequence is whose details I omit is sound and complete, capitalizing on again the structural properties of the calculi. We have an approach for abduction which sees an abductive problem just as an anti-sequent in classical logic, where we want to add up to a non-empty antecedent and additional premise, as you see in this slide, to get a provable sequent. previous approaches in the literature are concerned with Tableau. We use sequent calculus, and we obtained a nice result, or let's say problem to tackle, namely the fact that if we stick to the minimal hypothesis, the deductively minimal hypothesis, we obtain a formula. Which is not the expected solution of the abductive problem. As you can see, for instance, in this first case, okay, you have this anti-sequent. This is not provable in classical logic. If you add up Q or P, you can prove it, but you would like to have P. A rational agent seeking an optimal explanation for the goal formula would like to have P instead of P implies Q. And we have a proof theoretic procedure to capture these expected hypotheses systematically. And we have a justification, a tentative justification for this procedure, as well as a proof that it has not to do with with logical strength, in the sense that in the optimal solution, we do not drop something modulo logical equivalence. You can see that in this case, for instance, P is stronger than Q or P, and then we have rephrased the Quine-McCluskey method for the minimization of Boolean circuits to give a systematic proof of the fact that this notion of abductive redundancy is distinct from deductive redundancy. I will stop here, just saying that as far as the decision procedure for modified skeptical consequence, I had no time to present you. We have that the search for the counterexample is made by finite sequences of abductive inferences in this sense. So there is more than that, because we can apply this kind of hypersequent based approach to the case of AGM belief revision base generated. And we posit that further applications can be made, and it would be nice in particular to obtain sequent calculi which are strongly complete for default logics, and not only weakly complete as our hypersequent calculi, somehow exploiting previous work by Mario and Gabriele on controlled sequent calculi. I will answer your questions, or your if you are interested into further details. And here is some bibliographic reference. The work on abduction is already published, and the works on propositional default logics and AGM belief revision are under review. I thank you warmly for the attention, and thank you very much.